Hi, this is Chenming Jiang, and today I want to talk about how to handle the received signal. The ideal received signal should be like this, and we divided transmit signal into a series of timed period, and we use this to indicate each bit in turn. After we receive the signal and do the demodulation, we can simply get the transmitted signal out. But in the reality, there will be some noise also in it, and we will need to filter the noise out, and this is the hardest part of it.
Hello. In order to power the LED properly, we will need a bias T like Chris has explained before, which will bypass the need for a driver. We need to find an LED with a current limit higher than 80 milliamps, which is easily obtainable. This is important because the intensity of light is directly proportional to the current. Our LED will need a capability of at least 75 lumens, which is the average indoor intensity, and an option for an LED is shown next.
Last time I talked to you about having to work on a bias T that would split the RF signal and the DC voltage. The problem that we're trying to solve is that I need to work on matching the impedance of the coaxial cable and the input of the USRP so that there will be limited noise from the reflection of the bias T signal.
The photodiode amplifier operates by tying the cathode of the diode to the inverting terminal while grounding or reverse biasing the anode and connecting a feedback resistor and capacitor to the output. The current flows across a feedback resistor with a feedback capacitor to stabilize and prevent ringing, and this gives a voltage difference as the current of the photodiode times the feedback resistor. Stability, gain, and DC errors are considered first in the design of the photoamplifier circuit. Stability and gain can be compromised with the choice of op-amp and optical lens and filters. The biggest contributors to DC errors, output offset, are amplifier offset voltage, bias current, and the diode's dark current. Dark current is how much current the diode outputs in complete darkness. If the circuit is not fast enough, reverse biasing can be added, which helps reduce the diode capacitance, increase response time, but this also increases the dark current, which offsets the signal, increases the SNR, and is vulnerable to temperature drift. After this, the AC response of the circuit is analyzed for overshoot or undershoot. The feedback capacitor is then optimized for the best performance.